Now we'll move on to our first talk for today. Today's first presentation is brought to you by Gitarth on the topic of leveraging AI in defense, counter drones, and beyond. Gitarth is an AI software engineer at DroneShield, specializing in AI for defense and sensor fusion. With a strong background in artificial intelligence, he is also a dedicated mentor and academic. Gitarth actively contributes to the advancement of AI technologies and shares his experience through teaching and community engagement. This talk highlights the strategic role of AI in defense, specifically focusing on counter-drone measures and the expansive potential beyond. The conversation will then broaden to include TensorFlow as a versatile framework supporting various AI applications in defense, and Gitarth will also cover the essential aspects of deploying AI technology securely, leveraging Google Cloud security tools. Can I please get a round of applause for Gitarth? Actually, come up.
Have a mic for the. Yeah, thanks. Thanks for your kind words. Let's get started. Hi, everyone. I'm Gitarth, and thank you for joining today's session. Today, we'll explore some impactful role of AI in modern defense strategies. So let's get started. Let me briefly introduce myself. He already introduced. So just reiterating, I'm an AI software engineer at DroneShield. I'll talk about DroneShield in a bit. So I specialize in sensor fusion and vision AI, which is computer vision, and I develop cutting-edge AI solutions for counter-drone defense. I'm from UTS. I graduated from UTS recently with a university medal. I also teach at UTS, and my areas of expertise include computer vision, deep learning, and data analytics. So that's all about me. Now, okay. So the agenda for today is we talk about AI in defense. We'll also talk about UAVs. Then we'll talk about how we strategically deploy UAVs in military and how they're used in terrorism, something very recent, and the advancements of counter-drone technologies and the future of AI in defense. So today, AI is not just a tool, but it is sort of a big fundamental component in reshaping all the defense strategies. AI is used in data analytics. AI is used in enhancing situational awareness, precise decision making, and cyber defense. And lastly, but widely used in autonomous systems and robotics. Nowadays, we have drones which we could use with controllers, but with AI, we can say bye-bye to the controllers and they can fly autonomously. And that is something which is a big threat in terms of defense. And it's a big blessing for all the military people who would like to actually just pass on a mission to a robot which is gonna just accomplish it. So let's talk more about this. So what are UAVs? UAVs are nothing but flying robots. We could consider them as robots because they have mechanical parts. They have some software. They have some computer inside it. And what they do not need a human pilot on board. They are controlled remotely or autonomously with AI. They're used in a wide range of applications, including military services, civilian services, like all of us use it, surveillance, data collection, and a lot more. They vary in shapes and sizes. As you see, you could find small drones, which we use, and we could also find large drones like this, which are used in some other purposes. Now, these drones could be equipped with payload, could be a camera, could be something like a missile, a gun, delivery package, or some sort of, let's say, search and rescue equipment, if we're doing rescue. So they could include cameras, sensors, weapons, or some other equipment. Now, let's see, UAVs in military and terrorism. So they're transformed from more of a surveillance device into something which could be used for dangerous purposes, for attack, smuggling, espionage, collision, or probably nuisance. And it is also used in military purposes. As we see, there are a lot of drone attacks these days. Now, today, because we could use them for all sort of activities, they're also being used in terrorism. If you want to see some insights, here's a graph showing only 60 out of the 1,600 events by the end of 2022. There's not a single place in the globe where you don't have drone events or drone incidents. And these are classified into high priority. All orange events are high priority, which means something which caused power outage, bombs dropped, some other attack, people killed, and a lot of other stuff. Blue is all medium priority. And that's it. So a lot of damage caused by drones. Now let's see some more details about this. This is a graph. It's from my company. It's Drone Shield. So we saw 1,600 reported incidents by end of 2022. We could see we were at 20 cents in terms of stock price. Now, 2024, cut to May, we are at 134. We just crossed 140 yesterday, and we became a $1 billion company, Australian dollars. So you could imagine that this is the demand of a counter-drone market. 2022, it was 20 cents. Nobody was purchasing much counter-drone stuff. Now, it rose by about 450%. Imagine what is the exponential rise in the number of incidents which we saw right here. That's just 1,600 reported incidents. Forget about unreported ones. This just shows that there's an explosive surge in drone incidents in 2024, and we need something which could counter them equally. So let's get into what is counter-UAS in a bit. And with these stats, what I also want to show is Drone Shield is not the only counter-drone company. So there are others. So that also multiplies to the number of reported incidents, because not everybody is going to go to Drone Shield and buy. Most of them would, but probably not everyone. So let's see how it works. Was that good? So now, you saw a gun with the face of it blocked. It was something which doesn't fire. it is a signal jammer. So because drones operate on radio frequency, most of them, what we do is we jam those frequencies so the drones can't be controlled further. And with that, what happens is that the drone, according to how its computer is designed, would essentially either land or go back to the home position, or lose control and fall down. So those are the three extreme cases of what could happen when you jam. Let's say if the drone in current situation is not using a radio controller, we could also jam GNSS, which is all the GPS signals which it receives, which are required for a 4G drone to know where it is located at this point in time. Because they're not autonomous yet, these two jamming services work. And that is what that small gun does. There was another device, it was like a walkie-talkie, that was just telling the operator that there is a drone somewhere around. It is actually a patrolling device. We call it RF patrol. And there was some other device, a big overhead device, which we call DSX. That device essentially is a bigger version of that radio frequency patrolling device, which also tells you what direction the drone is, probably what drone it is, and where the controller and home location of the drone is in certain cases. So those are all the devices which we develop. There's more than that. The further development into this is that we also have radars and cameras which you can attach to these systems, and they would essentially detect flying objects. Camera would also detect that, so we could detect what payload it is carrying, what size it is, what model, make, type, all sort of details from the camera, radar, and the radio frequency sensors. And then we can integrate it with any counter defense provider. We develop counter drone jammers. There are people or other companies who develop microwave solutions, so you just burn the drone in the air, or the kinetic solutions where you fire a missile or something, or another drone which would just collide with the drone. So we could also integrate with such tools. So that's all about what counter UAS looks like in today's world. Now let's see how we actually make that work. So there are 4 steps in this. First step is to detect. So we need to detect whether there's a flying object in the sky or not. So we detect using multiple sensors. First, foremost, radio frequency. Most common drones fly using radio frequency sensing or signals. So we detect radio frequency signals. Next is radar. If the drone, for example, doesn't use radio frequency, radar is definitely going to catch, because radar catches any movement, right? So we use radar. The next sensor is camera, because if radio frequency is telling you that there is a drone somewhere, radar is telling you there is a flying object somewhere in the sky, you still don't know, based on only radar, whether that's a drone, that's a bird, that's an airplane, or that's something else. We need camera to confirm whether that's a drone or not. So we combine all of these 3 sensors. Now, each of these sensors have some AI within them. Radio frequency sensors, as you all know, we all use radio devices. There's walkie-talkie, there's other radio communication happening, there's FM radio, which we listen to in the cars. There's airplanes communicating using radio. There's a lot of radio usage. Out of that radio noise, you need to figure out which is the drone signal and which is not the drone signal. And to do that, you need some AI, some sort of classification, to determine whether that signal is actually drone or controller or something which we are not interested in. So that is where AI works in radio frequency. Then next step is radar. Radar also gets all sorts of movements classified, whether it's a car moving, whether it's a person or a bird or anything. So radar also needs to do some sort of classification to know whether the trajectory or the behavior of that particular object it's detecting is similar to that of a drone or something else. So likelihood of that object being a drone or not. So that is again radar. And same thing with the camera. Camera needs to classify whatever it's looking, what object that is, drone or a bird or an airplane or anything, and where is that in the frame, and keep tracking that. So that is all about camera. So there's 3 main sensors for now, which we deal. Now, for example, you have all of these 3 sensors. They're detecting a drone. Radio frequency tells you the drone is at certain location. Radar tells you the drone is at certain location. Camera also tells you that it's at certain location. Now the problem is that all of these 3 sensors, because they're sensors, they can't be 100% accurate. So they would have some sort of an error. So all of these 3 points, if you put on a map, would look a bit different. They wouldn't be pointing to the same exact location. So you need some way to combine that detection and generate one unanimous output. That is where we use another AI, which actually uses all of these outputs and combines that. That is what we call data fusion or sensor fusion. We could do non-AI ways, but there's enormous amount of data. The scenario keeps changing. We need AI to support that. So we do that. And then after the AI-powered sensor fusion, we use that fused data to do some more analysis using another AI algorithm, which would essentially take all of these attributes, which is location, altitude, distance, pose, speed, path, trajectory, payload, proximity, to analyze the behavior of the drone, or whether it's a drone or not a drone based on, let's say, camera says it's not a drone, radio frequency says it's a drone. You need to decide whether it's a drone or not a drone. So it decides that, and then it essentially computes whether that object poses any threat to whatever you're protecting or not, based on the proximity to the place you're protecting, or whether it's carrying some payload, or whatever. There's multiple factors. So that's another model. So a lot of AI is being used in counter-UAS just to do surveillance. We're not even talking about jamming. And just until this step. So detection and tracking is just the sensors. You want to identify whether it's a threat or not. You need to fuse them and get some data out. And then once you identify that, yes, it's a threat for something which we're protecting, we need to think of options to defeat, which you already saw. There's a gun, there's a jammer, there's bigger jammers, there's heaps of options to defeat. But what about this thing, which would happen in a fraction of a second? Because if a drone is flying at 100 kilometers an hour, or even more, the world record is about 400 kilometers an hour. If something is flying at that speed, you need the system to work super fast. And that is why AI, because algorithms are slow. You could jump up the course, make the system faster, but not as fast and as accurate when you use AI, because we could definitely collect a lot of data, do some processing, use some AI models, use it with enormous GPU computation, and then get there. So that's the how-to of counter-UAS on a high level. So let's see how to simply detect a drone, the easiest way to detect it, and not getting into all of this complex stuff. Basic, just use a camera. Very simple. You see a flying object, you see where that is, right? And then you see what that is. It's a drone, it's a DJI M600, doesn't have any payload, it's just a drone flying somewhere in the sky, right? So we use deep learning and CNNs, computer vision, to detect, and this would just help in real-time visual assessment of what that is, and that's it. So this is the simplest way to detect a drone out of everything else. Now, how to do this? How to achieve this? there is simple stuff as well. It's called object detection. That's computer vision. What do we do? If you want to know whether that object is a drone or not, you do classification when you get an image. You could say whether that's of a drone or not. So that's one image. If you want to localize it, okay, where is the drone in the picture? You could essentially have a bounding box to get the location. Well, that is not the ideal case scenario, that you would just have a drone in the picture. Is that the case? You would also have birds or airplane. So that wouldn't work. You would need multiple objects. So what we do is we use object detection or segmentation. For us, we just need to detect where the object is and keep tracking. So we would just use object detection, where we detect some objects, then we classify it. Okay, I could see some objects in certain locations. Now I need to classify it. This one is a bird, red one is a drone. That's it. If I wanted to go more further into it and already decide what are the exact boundary or border of that object, I would do instance segmentation. So for our job, we just need to detect where the drone is and whether that object is a drone or a bird. We could essentially go ahead with object detection. Now for AI, you need to provide some data. It's data hungry. What data do we provide? Image, the box coordinates, so x and y values of the box coordinates, and the class. So it's a drone or it's a bird. If it's a bird, where is the bird? So the coordinates in the image. That is all the data we need. Now, how does it work? I know that's a bit complex, but this was the simplest. This is the oldest object detection architecture, which is still being used in the industry. So what happens? You give an image to some AI. This is an AI model, the skeleton. It uses something called convolutional neural network to extract features. What are features? Features are essentially something like, okay, if it's what color it is, what size is it, in simple terms. Does it look like a drone? Not, and heaps of such things. You keep that in a map called a feature map, so like a table or something. And then what we do is, out of that features, we have another tiny model which just decides the objectness. That, okay, I want to see whether in a certain region, is there any object or not? And then if there is any object in any such region, I just save that region somewhere aside. That is called region proposal network. It is going to use sliding windows, find some regions simply, and then save those regions that I saw. I think that out of the background, I could see some regions where there are some objects. We don't know yet what objects these are. And that gives you regions, which we call boxes, on your feature maps, which is essentially proposals from the region proposal network that, okay, I suspect that on these few locations, there are some objects. Then we take all of those regions, essentially crop that image, and what do we perform? Image classification. That if that was a big image, I cropped this small bit, I just pass this to another model to say, what is this? It's going to say it's a drone. That happens in the last box. So first box is to find objects, whether there's objects or not. Next box is to find whether that object is of my interest or not. It could be something else because it's an object. It could be butterfly flying, which is not in my data set. I'm just interested in drones and birds. So I would say, I would just disregard that box. But if it's anything from drone or a bird, I would essentially save that and pass that as the output, saying that I see one bird and one drone. That is how object detection works. This is very complex, right? So we need GPUs. We need some framework to deal with, to develop AI. And that is where we have Google Cloud. We have TensorFlow to train the AI models, develop the AI models, design the network. We have Vertex AI to process the training task, process data. We have some other Google Cloud components which work around that. So let us see quickly on what is a complete life cycle of AI on Google Cloud. So this is a common diagram. If any of you knows DevOps or a software life cycle, you would relate. Now, this bit is just a software life cycle where you code, you build, you test, and then you release, people use it, deployment, then you monitor it, you get some errors, you plan it, and it's just a cycle back. So that's DevOps, normal software practices. With machine learning, you also get two more components to it. One is data, that you need to collect data based on the problems. Then you need to curate, which is modify it, transform it, also validate whether that data is good or not, and then finally train a machine learning model, evaluate, which means check if it is working well or not, and then pass it to the software, for the software guys to put that into the software and then do the regular DevOps. All of this could be done using Google Cloud easily. Data collection, you could use PubSub, BigQuery, cloud storage to do the collection essentially, and storage. Then to curate, to label data, you could again use data labeling from Vertex AI, some AutoML stuff. Then for transformation, you could essentially use no to low-code pipelines from Google, Dataflow, Dataproc, BigQuery, Cloud Composer. There's a lot of tools we could use. Then to validate the data, you could use Vertex AI plus BigQuery to see if your data is actually proper. Then we do some exploratory data analysis, which is we see, okay, out of my images, how many of them actually have drones? How many of them actually have birds? Because let's say I'm interested in drones more than birds. I still need to have equal amount of data so that my model learns to distinguish properly within the drones and birds, right? So you need to do that analysis of the data. If it's not good, you need to reiterate, recollect, fix it, then again explore and see if everything is good. We could maintain a dashboard by using the Looker Studio, which is dashboard tool, where we could actually maintain a live tracker of how the data looks like. Then we come to the machine learning part, where we would use TensorFlow to build our models. Then we would use Vertex AI training, AutoML, or BigQuery ML, depending on what sort of model you have, to do the training. Then we would use evaluate. So we have TensorBoard from TensorFlow. It also has a Vertex AI support. We would do evaluation. And we have a model registry in Vertex AI, which is used to save the model and do the versioning. So this green bit is mostly Vertex AI or BigQuery. If you're dealing with CSV, XML, text form of data, it's BigQuery for you. So that's machine learning bit. Next is DevOps. It's again cloud functions, cloud run, and other stuff to essentially store your code. As you saw in the keynote, we also have some IDEs from Google AI now. So that is going to be added into here. And then we have operations, which is deploying the model. So if you want to deploy it on a mobile phone, you would essentially convert your model into a TensorFlow Lite or a TensorFlow JS, or if you want to deploy it on K8, you would convert it to Kubeflow. Or you could create an API, which is managed on Vertex AI itself. So there's heaps of ways on Google to deploy a model securely. And then to operate, essentially to monitor how it's working, you essentially have dashboards. If you want to do batch inferencing, which is process a lot of data at once, let's say every night I want to process something, you use batch inferencing on Vertex AI or BigQuery. And you could serve your model somewhere on an endpoint using any of the Vertex AI tools or K8s. So that's Google Components again. And to monitor, you again have model monitoring from Vertex AI, so how your model is performing. And if someone could report that your model didn't do well on my data, it's wrongly classifying stuff, you could take that as a feedback and then goes back to data again. So that keeps on happening throughout the life cycle of a machine learning project. So that was it. Now let's check that out in more detail, simple words. If you want to start an AI project on GCP, how would you do it? We're not running a boot camp, so we go like this. If we were, I would actually do this by hands, but doing all of that is a big task. So we could do a longer duration workshop sometime to know how to use this. So we need some deployment systems. So we could use Service Catalog to have some deployment systems. Then data sources, which produces data, could be cloud storage, for instance of my project, which is images. Or I could store my images in NoSQL database somehow. So query could also work, because I could query images as well, as far as I know. Then we need interactive development environments. So something like a good IDE, VS Code, with potentially Gemini into it, who already knows how to write models in TensorFlow using Python. That would help. So we do all the data extraction, data validation, exploratory data analysis, model training in the development environment. So these are all different components. Then you need production and non-production environments to make your models operational. So once you have a model, it gets into some model registry. Your code gets into the code registry. If you have a model, you have some pipelines running. Whenever you get a new model, validate the model, then you serve the model using model serving, and keep monitoring the model, right? If you get a feedback, retrain, revalidate, redeploy, right? So that's a production component. And then you also have some other services where you store your features. If you think that, okay, this model was really good, let us analyze the model further on why and how this model is working. We store those features. Let's say if a model is really good, we store it in a model as a model garden. So I could have a lot of models stored, which you all could access, and a model registry, which is version management for my AI models. So that is a complete project, AI project, from data sources to deployment, just by using Vertex AI and some other cloud, Google Cloud tools. So this is all we need for a project. Next is, this is how we actually deploy it, how it works. Those were components. How does it work? You are a user. You have a Git repository somewhere in GitHub. Then what you have is some deployment services or cloud storage. And you have a pipeline, as I discussed. You get the data, validate it, pass it back to the feature store, because you have all the features in there. And then you train the model. So that is a pipeline. This pipeline orchestrates everything from start to end, get the data, train a model, deploy it, and that's it. Monitor. Something gets wrong, go back to the pipeline, feature store, model training, evaluation, and then deployment. So it's a complete operational project. This is how it actually works under the hood. And in context to defense, as you know, we see a lot of new attacks happening. The diversity of the data keeps on changing. So it keeps on increasing. And we keep getting new data every now and then with new drones, with new behaviors, and with almost everything new. Because the drone developers are potentially those who carry out these threatful activities also know that there is counter-drone systems in place. And it's the same case with the hackers and the ones who develop security practices. So you need to be one step ahead, otherwise you fail. So you need to keep training, and this is the only way to keep training the models. Now, because it's defense, we need to think about security. We never saw how to make all of that secure. If it's not secure, anyone could intercept my feed and show a blank sky. So that's all about security. What do we do there? We essentially have security at all different levels. At the interface level, we have repositories, we could implement security. Deployment level, we have infrastructure security, containerization, networks, we have VPC, virtual private cloud, firewalls. We could have access management, secure key management. That's all about how to make things secure and encrypted. You could also have a detective, which is to detect whether the system is having problems or not, and to prevent. Okay, so let's move to the next part, which is what is next for AI in defense. One is AI-driven cyber defense, and the next is autonomous robotic units. So let's see what we have. Google recently designed this. You could have Duet AI for security. You could have a large language model for security. You could also bring your own AI for security. So AI is also doing security. And lastly, what we have is enhanced robotics. I'm just gonna play this 1-minute video. What it's essentially doing is, that's a drone. It's flying the drone to a position, telling an LLM, which is something like ChatGPT, to remember the positions. So it's setting a map locally in a computer. So once it's set, it's going to ask that, remember these positions, and now just comb the area. So do something like a surveillance. And it's going to essentially do the surveillance. So that's just the beginning of future of AI with robots. So it started doing some code. Because it's generative AI, it's not going to succeed in its first attempt. Got a lot of errors. You just told that, okay, that's not the right function. It said, okay, use the right function. And now you see, it is actually flying and covering the complete area. So that is the future of autonomous robotics. This is where still the human is communicating every step. There would be future where you essentially provide a satellite map, explain the mission, no network, no GPS, no radio controllers, and it would just use onboard sensors to and the LLM to accomplish the mission all by itself. That's the future we're expecting, and probably 10 years from now. And final remarks, I think I spoke a lot. So AI is not just transforming defense, it is just setting a nice stage for a future where security is smarter, faster, and more reliable. We do need security. I'd like to acknowledge Google Cloud Sydney for inviting me. Also Drone Shield for a lot of data, statistics, videos, and IO Extended. And last but not least, stay connected. If you want to connect, that's my LinkedIn. And we are hiring at Drone Shield. We keep innovating, as you saw. We need everyone from accountants, designers, full stack engineers, AI engineers, almost mechanical engineers, field testers. We have space for everyone, but we need skills. So if they're genuine skills, there is a role for everyone. That's the link for current positions. There's an expression of interest as well. And that's my LinkedIn. Thank you.
Thank you so much, Gitarth. So do we have any questions for him?
Yes.
Two simple questions. For the recognition of the drone, sometimes drones are being attacked by birds of prey. So if you looked at it, can your system detect that it's actually both a bird and a drone, because the bird is obviously on top of the drone? And secondly, with that future you mentioned, because it's autonomous, there's therefore no signal from a controller. You're not able to intercept that signal. How will you then defeat it when it's actually operating by itself? And presumably, that drone, when it's completed its mission, knows I need to go back to my home base. So that's my two questions.
Okay.
Sorry. Before you answer, we'll take exactly 3 questions in the interest of time. So that's the first one. We'll take only 2 more, just to make sure. Yeah, go ahead.
So I'll answer quickly. The first question is whether we could detect both drones and birds when there's a flock of birds, or probably a bird flying on a drone or something like that, or in overlapping situations. We could. That is why if we have a lot of diverse data, we could train a model. We just need to modify the architecture, and we could detect it. We could do much more than just overlapping cases. We could detect multiple drones looking like bird. We could detect that as well. Your next question was it? Autonomous drones, yep. So how to defeat them? For us as a company, I can't tell you. We need to think about it. Probably we've already thought about it. But there are certain people or certain companies who exist. Because we're doing non-kinetic defense, we need to think about it. If we talk about kinetic defense, you could just use our system to detect such a drone and fire a missile or just burn it in the sky itself. But if you want to essentially jam it, we need to intercept its own internal network on which it's communicating, and then do whatever we want to do. So probably hack it. So that's a short answer to that. Okay.
I can ask a question.
Yeah.
So one question is that why do you use TensorFlow rather than, let's say, PyTorch or YOLO or other models of computer vision? And the other is that basically how many antennas you need in order for RF sensing and localization, because I thought one is not quite enough.
It depends on, radio frequency works on different bands. There's different bands for different antennas for different bands. So our system could connect 3 antennas at a time and just capture a complete band. We could go 2.5 gig, 5 gig, and much more within just those 3 antennas. So we connect them. So that's one, so we could detect. And about the libraries, you could use any, but TensorFlow personally is more versatile when it comes to deployment on various diverse environments.
Now, last question.
Hey, so I had a particular question regarding like the recognition of the drones. So I was just reading recently about the adversary machine learning of like AIs and stuff, and over there, like if some stickers or something were to apply to like drones, or like they were to cover in like some other material that would deceive the AI in your like drone detection systems. Well, like how is Drone Shield or like any other company gonna take care of that?
We have redundancy. We have redundant sensors.
Mhm.
There are much more sensors which we also integrate. There's acoustic sensors. There is other sensors like infrared. There's just, it's just not limited to 3 sensors. If it is stealth in radar, but it still uses radio frequency, we detect it. If it's adversarially created, camera can't detect it. Other 2 or 3 sensors could detect it. There is a way. You could detect it. And if you could detect it, you could kill it. So, yeah.
Sorry to cut the Q&A short, but yeah, Gitarth will be staying behind if you want to ask him some more questions. And we do have a presenter gift for you.
Thank you so much.
You have one more round of applause for Gitarth.
Thank you so much.